Hey everyone, this is Connor Mead with the Calculation Center and with another video in our linear algebra series. This section is on inverting matrices and the properties of the inverse matrix. Okay, so here we've got a 3 by 3 matrix A, and we've got three questions here. We want to check if A is invertible, compute the inverse of A, and use it to solve this system of linear equations. Okay, and let's just recall that A inverse is the matrix such that A times A inverse is equal to A inverse times A is equal to the identity matrix. And in our case, we're dealing with 3 by 3 matrices, so the identity matrix will look like this. If we were dealing with 4 by 4 matrices or something like that, the identity matrix would be the matrix with zeros everywhere. It would be a 4 by 4 matrix with zeros everywhere, except for ones along the diagonal. Okay, so let's see how we do this. So the first step is we want to check if A is invertible. And to do that, we compute the determinant of A, if we remember, if you've seen the video on that section. So let's just quickly compute the determinant of A. And remember, if A is not invertible, A inverse does not exist. So for this sentence to make sense, A had better be invertible. So the determinant of A is we look at the top left entry, write it down, and take the determinant of the remaining submatrix, 2, 3, 0, 2. If you're having trouble with this, feel free to pause the video and go off and look at our determinant video. Determinant of 0, 3, 1, 2, and plus 1 times the determinant of 0, 2, 1, 0. Okay? And quickly computing these, we'll get this is 1 times 4 minus 2 times minus 3 plus 1 times minus 2. So overall, this is equal to 4 plus 6 minus 2 is equal to 8. Okay, so the determinant of A, since it's not 0, this implies A is invertible. A matrix is only not invertible if its determinant is 0. Okay, so you can compute the determinant to check if any matrix is invertible. Okay, so that's the first question. A is indeed invertible. Now let's compute A inverse. I'll just get a copy of A down here because I'm going to need it. So the idea here is that this is A. What's A inverse? To compute A inverse, the idea is we're going to write down our original matrix A, 0, 2, 3, 1, 0, 2. We're going to draw in the augmented matrix equation bar line again, except instead of usual, we're not going to just put a single column of numbers here. We're going to put in the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, the idea here is if this here matrix is A and this is I, the idea is if we do a bunch of row operations such that it now looks like I on the left, we'll actually get A inverse on the right. Okay, so we want to do a bunch of row operations so that this matrix here turns over to this left-hand side of the bar, and then we'll see that the resulting pattern that comes on that from the right is the inverse matrix of A. Okay, so let's do this, and we reduce this left-hand side to the identity matrix as we always do using the pivot algorithm. So we put this here, put 1 here. We don't need to, and we want to turn everything below the 1 into a 0. So let's go like 1, 2, 1, 1, 0, 0. The second row won't change because that's already 0. And the third row we need to subtract off the first row. So row 3 is going to row 3 minus row 1. Okay, so this becomes 0, minus 2, 1, minus 1, 0, 1. Right, because we subtract off this first row from the last row. Okay, now our next pivot is this 2. And we're going to want to use it to turn this minus 2 into 0, so obviously we've got to send row 3 to row 3 plus row 2. That should do our job. Okay, so what do we get here? We get 1, 2, 1, 1, 0, 0, 0, 2, 3, 0, 1, 0. We haven't done anything to change row 1 and row 2 in this step. So we get 0, 0, 4. And what do we get on the right-hand side? We're adding the middle row here to this bottom row down here. So we get minus 1, 1, 1. Okay? And now we're done with Gaussian elimination, so we just want to go back up and get rid of the elements above our pivot entries. Okay, these are our pivot entries. I'll also point out that if you try and do this process for a non-invertible matrix, you'll get basically a row of zeros here equal to a non-row of zeros here, and that'll be you won't be able to proceed with this process from here because you'll never turn it into the identity matrix. So you can identify that a matrix is non-invertible if this method fails as well, but usually it's easier to just compute the determinant. Okay, let's try and get some common factors here. So we can use this 4 to turn things above into 0. So let's go 4, 8, 4, 4, 0, 0. Let's send this to, I guess, 4 times this equation will be 0, 8, 12, 0, 4, 0, and 0, 0, 4, minus 1, 1, 1. So all I did there was I sent row 1 to 4 row 1, and row 2 to 4 row 2. And I did that so I could use this 4 to get rid of this stuff without having to deal with fractions. If you want, you can just divide across by 4 and subtract off and deal with fractions and be careful, but I think that method often leads to more mistakes, so I try to avoid it. Okay? But now this should be pretty easy to reduce this system of equations. So let's send row 1 to row 1 minus row 3, and row 2 to row 2 minus 3 row 3, right? Because this is a 12. And let's see what we get. We got a 4, 8, 0, 8, 0, 0, 4, 0, 0. And that's the important thing is what happens on the right-hand side of this bit, okay? So row 1, we're subtracting off row 3 from row 1, so this becomes 5, minus 1, minus 1. We're subtracting off 3 row 3 from this, so it's 3, 1, minus 3, and this last row won't change, minus 1, 1, 1. Okay? And lastly, we just want to get rid, I say lastly, we now want to get rid of the entry above the middle pivot, this one, and to do that we obviously just send row 1 to row 2, row 1 minus row 2, and that should do the job. So then we get 4, 0, 0, 0, 8, 0, 0, 0, 4. Now row 1 minus row 2, this is 2, minus 2, 2, 3, 1, minus 3, minus 1, 1, 1. Okay? And now we can divide across by all of our middle entries to turn this into the, we will remember that we want 1s on this left-hand side of the equation, so we can divide across by these entries to get them to become 1s. So row 1 gets sent to a quarter row 1, row 2 to an eighth row 2, and row 3 to a quarter row 3. Okay, and this gets us the identity matrix on the left. And what we get up here, the first row is divided by a quarter, so this is a half, minus a half, 3 quarters, 3 eighths I should say, 3 eighths, 1 eighth, minus 3 eighths, minus a quarter, and a quarter. And then this matrix here, I guess we can just grab it. This is our inverse matrix of A. Oh, sorry, these shouldn't be here, obviously. This is what A inverse is. Okay? And now the last step here is we want to, we want to lastly use it to solve this system of equations here. So let's just grab this down. And I guess the important thing to notice here is this equation is equivalent to the equation A applied to the vector xyz. So xyz is a variable vector, is equal to 101. So essentially we're solving this system of linear equations here. If you're not comfortable in changing between matrix equations and linear equations, you'll probably have to check out an earlier video. But assuming we can solve this, we should be good to go. So let's move down a little bit. So how can we solve this equation using the fact that we know what A inverse is? Well, this equation, since A inverse times A is the identity, this implies that A inverse times A applied to xyz is equal to A inverse applied to 101. This is just applying A inverse to either side of the equation from the left. These two cancels, so you just get xyz, because A inverse times A is just the identity matrix, and the identity matrix doesn't do anything, is equal to A inverse times this, so we just have to multiply this by A inverse, and we'll get our answer. 1/2 minus 1/2, 1/2, 3/8, 1/8 minus 3/8 minus 1/4, 1/4, and 1/4 applied to 101. Okay, and now if you've seen the video on multiplying matrices, we can just sort this out immediately, and this is equal to 1, 0, 0. Okay, so this has been Connor Mead with the Calculation Center. Hope to see you in the next video, and hope this all made sense.